Okay, hope everyone can see my screen. Welcome to the workshop. My name is Chi. I'm a principal researcher from Microsoft Research. In this 3-hour workshop, Qingyun, Louis, and I are going to introduce a fast AutoML and tuning library FLAML and some related products. FLAML started as a research project in Microsoft Research and has now grown to a popular open source project. Within 1 year of release, it has got nearly 2,000 stars and 500,000 downloads. The goal of this workshop is to teach everyone how to use our tool in your work and make your ML ops life easier, including how to use FLAML to easily and quickly find good machine learning models for your application, and how to leverage the rich customization choices to meet your last mile requirement for successful deployment. We will provide code examples, demos, and lessons learned from customers. No matter whether you have experience in AutoML or hyperparameter tuning before, we hope that when you walk away from the workshop, you have a good idea what FLAML can help you achieve in your daily job. Here's an outline of today's agenda. In the first half of the workshop, I will first give an overview, then Qingyun will introduce the two major APIs of FLAML, which cover two types of use cases, task-oriented AutoML and tuning user-defined function. We will have a mini Q&A session after that. In the second half, I will first introduce two relatively new features of FLAML, including zero-shot AutoML and time series forecasting. Finally, Qingyun will briefly introduce some ongoing and future work, and in the end, we will leave some time for discussion. Feel free to ask questions during the tutorial via the chat. In the discussion part of the workshop, we'd like to hear from the audience what's your takeaway and what are remaining challenges you'd like to solve or additional features you desire. In the first 15 minutes, I will give an overview, including the background of AutoML and hyperparameter tuning, the benefits of deficiency of AutoML and how FLAML addresses some of the deficiencies, etc. Recently, McKinsey identified 7 cross-industry trends that reshape the future of markets and industries in the next few decades. And 2 of them are related to applied AI and software 2.0. A growing number of developers now have access to machine learning techniques, and there's a strong interest of using them. A general machine learning workflow can be roughly characterized in this picture. To use machine learning in an application, we need to get the data for that application, prepare the data, train models using the data, and evaluate the models. Before the models meet the deployment criteria, we need to keep iterating the model training. There are a lot of decisions and choices to make for a general developer to find a good model. For example, we need to choose the right training algorithm for our data and our task. There are so many machine learning libraries like scikit-learn, XGBoost, LightGBM, PyTorch, TensorFlow. Each of them offers many knobs to tune to optimize the model performance. For example, for LightGBM, we need to choose the number of estimators, number of leaves, learning rate, etc. How many developers are confident that they can make the right choice for all these decisions for their data at one shot? So this is usually a trial and error process. As more and more teams start building millions of machine learning embedded applications, it adds up to a large cost to manually tune the hyperparameters and choose the right machine learning model for every task and every dataset. And even with the huge effort of manual tuning, very often the decisions made are still not optimal, and significant model performance gain opportunity is left on the table. Also remember, it's not just the one-time cost for one application. Every time the code, data, or deployment criteria are updated, the choices could become invalid, and the optimal configuration could change. AutoML tools automate this process and empower developers who don't necessarily have expertise in machine learning. The goal is to remove the hassle of manual tuning for data scientists and engineers. We have seen a rapid growth in AutoML software, including open source, cloud providers, and startup companies. The market size forecast in 2030 is about $15 billion. Okay, what do users think about AutoML tools? There's a nice user study done by UC Berkeley. They summarized the benefits and deficiencies according to users' feedback. On the positive side, the AutoML tools empower novices, standardize the machine learning workflow, improve the efficiency in model building and prototyping. They also foster learning and sometimes even prevent suboptimal results due to idiosyncrasies of machine learning innovators. These match pretty well with our own observations and other industrial reports. On the negative side, there are multiple complaints. Some are about software usability, such as extensibility, customizability, transparency, and comprehensive support. And some complaints about performance. One common performance complaint of existing AutoML tools is they often consume large computational resources, especially for large-scale training data. That causes system failures, meaning the system is not able to return a usable model. Many users have to run experiments on limited computation resources, and they have to modify the model search space to reduce the total runtime. Some users would even revert to manual development for large models, which is a big setback. Besides the performance issue, if you look at those tools, they either lack enough customizability or require too much effort in making too many hard choices for users and go against the purpose of AutoML. There's no middle ground like, I only want to customize one or two things and I want the library to decide the rest for me. And for different users, the things they want to customize are different. FLAML strives to address some of these issues by being fast, economical, customizable, and extensible. These different aspects are not completely orthogonal. For example, the extensibility and customizability require our solution to be sufficiently general and robust. That increases the performance challenge because we need to be performant in all different situations, including different learning tasks, models, and datasets. Once we have a high performance and robust tuning layer, we are able to build the AutoML solution transparently on top of the tuning layer and the machine learning layer. It's something that seems to be trivially natural, but actually a unique feature in FLAML. It enables a smooth customization experience all the way from the most automatic AutoML experience to the most flexible tuning experience in the same library, covering all the middle grounds. That turns out to be a big deal and is the most important reason for adoption besides the performance advantage. Okay, installation of FLAML is very easy with a pip install. There are several ways of using FLAML. Task-oriented AutoML is usually the first recommended way for all the users, no matter whether you're an expert or a beginner. It can be used as a scikit-learn style estimator in just 3 lines of code. It requires minimal input. You only need to specify training data and task type to use it. Customizing the optimization metrics, learners, and search spaces, etc. is very easy. There are other scenarios where you want to use a different API to run generic hyperparameter tuning for fully customized function and search space. For example, when your machine learning task is not one of the built-in tasks, or when you need to directly optimize the performance for downstream application. Zero-shot AutoML is a new feature to offer a seamless way to leverage AutoML for the commonly used classifiers and regressors, such as LGBM and XGBoost. For example, if you're using LGBM.LGBM regressor as your current learner, all you need to do is to import the LGBM regressor from FLAML.default. Then you can use it just like the original LGBM regressor. Your other code can remain unchanged. When you call the fit function from this new regressor, it will automatically instantiate a good data-dependent hyperparameter configuration for a dataset, which is expected to work better than the default configuration. The intuition is that instead of running full hyperparameter tuning from scratch every time, we can leverage the tuning experiences in similar tasks before. And for AutoML providers for a particular domain or organization, they can learn and customize defaults for users' tasks or learners or metrics based on their own tuning experiences. FLAML optimizes for low computational cost in finding accurate models. The main idea is to design an efficient search order to control the overall trial cost before finding low-error models for both hyperparameter tuning and AutoML. The full-fledged AutoML system involves a bigger optimization problem over more factors than hyperparameters. The additional factors include the learner, the size of the training data, and the sampling strategy. And we need to consider the joint impact of all the factors in the trial cost and the model error. Here's a picture about the research technologies invented in FLAML. We begin with inventing a simple and provable local search algorithm called flow-square. And with that, we develop a cost-frugal optimization method, CFO, which has superior empirical performance. That's the core hyperparameter optimization method of the library. The main advantage compared to other hyperparameter optimization methods is that it can use small computational cost to find a highly optimized model. We further extend it to combine with global search and make a framework called blend search. It's able to handle more complex search space well and is suited for parallel tuning. For tuning online machine learning models, we developed a technique called charger. It also leverages CFO as a submodule. FLAML is the first and only AutoML library that supports online machine learning models. And recently, we invented a new meta-learning approach to enable zero-shot AutoML. It leverages offline tuning experiences to learn data-dependent default configurations. So it can automatically recommend good configurations for new tasks without tuning, pushing the AutoML cost to the lowest possible. We'll cover this new feature in later parts of the tutorial. What profession benefits from FLAML? The top two segments are data scientists and software engineers, followed by domain experts and machine learning researchers. Most of the users have at least 5 years of programming experience. There are also users who have merely 2 to 4 years of programming experience. There are many internal and external use cases of FLAML in different application domains, like CRM, security, banks, marketing, civil engineering, networking, insurance, and healthcare. In general, the impact of FLAML is in 3 folds: accuracy, productivity, and R&D. The models found by FLAML are successfully deployed in many products with high accuracy. FLAML saves huge amounts of dev time for both developers and data scientists. The ability to conveniently incorporate new algorithms into the existing pipeline, allowing easy extensions and being able to get large-scale parallel tuning makes FLAML play a big role in R&D of some big enterprise customers. How does FLAML fit in ecosystem? It works well with popular open source machine learning libraries like scikit-learn, PyTorch, Hugging Face, as well as cloud services like Azure ML. We had a collaboration with Anyscale. We integrated FLAML with Ray for distributed hyperparameter tuning. We integrated with ML Flow for logging, etc. I also want to mention that Microsoft offers multiple ways to do AutoML, as mentioned in this blog post on the right. FLAML can be accessed in 4 of them. So I want to talk about the Visual Studio and .NET offering a little bit. The core technology of FLAML is shipped in Visual Studio 2022 for .NET developers. It's ported to C# and integrated in ML.NET Model Builder. It's a tool in Visual Studio with a graphical interface. A developer without machine learning expertise can also easily use it to build a model from their own data and use the model in their application. Besides Model Builder, there are also code-first approaches to AutoML with ML.NET and C#. FLAML is the engine powering all these tools. FLAML gives a huge performance boost to the AutoML offering. For example, it greatly improves the number of models explored, reduce the timeout error rate by more than 50% with small time budget, and improve the accuracy significantly. So now I'll hand over to Luis to do a demo about the FLAML AutoML technique in the .NET products.
Perfect. Thanks so much, Xi. Hey, folks. Apologies for the early technical difficulties. My name is Luis, and I'm the program manager for ML.NET. And I just want to kind of preface this by saying that we're so excited to have been able to partner with Microsoft Research to bring FLAML over to the .NET community, as Xi sort of showed in previous slides. In terms of the folks who are using AutoML, in terms of programming experience and basically what their job title and day-to-day is like, that sort of scenario where AutoML fits really great is good for our sort of audiences. So ML.NET is the open source framework for machine learning inside of .NET. And most of our customers or our users, they tend to be developers, so they're not data scientists. However, they would still like to be able to use data science and machine learning to solve problems in their day-to-day, right? And that's kind of where FLAML and automated machine learning comes in, which is, you're able to automate that training process and at the same time be able to generate these models without having to think too much about, picking the right hyperparameters, picking the right algorithm, as long as you have, and I think we're going to talk about it a little bit later, which is this task-based machine learning, where kind of what you're seeing here is the model builder tool inside of Visual Studio. The task-based automated machine learning lends itself really well for these scenarios. So for example, if I'm a developer and let's say I want to gauge the performance and take a look at and forecast what the demand is going to be on my systems, I can just come here and say, oh, I want to do or try to solve a value prediction scenario, right? In this case, I'm going to kind of walk you through a typical sort of hello world type of scenario to show you how we use FLAML and AutoML inside of our tooling. So again, I'm going to go with the value prediction scenario, and you can see that you have different options here. In this case, we can only train locally in our CPU, but you also have options here to train on Azure as well. So that's typically for more work-intensive or resource-intensive workloads. But if we go to value prediction here, we can select our local CPU. If we go over to the next step, you can see that basically at this point, you just select the file with the data that you're going to train with. You select what your label is. In this case, it's going to be a fare amount. We're predicting taxi fares based on the different features here. And then at that point, we just provide a time budget, right? So that's the only parameter that a user here has to essentially, enter, right? That's the only thing that they're going to modify here. In this case, I already trained this, so I selected 60 seconds. I can, obviously, so the more that I give it, then the more chance it has to find the right model. And you can see that it found within the time budget a pretty good model, at least from an R-square metric, which is what we're optimizing for in this particular case. But at the same time, 39 models were explored, which is absolutely amazing in such a short amount of time. To give you a little bit of context, before we used FLAML, we actually already had our own AutoML implementation inside of ML.NET. And some of the challenges, which I think she already kind of touched on, we ran into a lot of those, right? We couldn't find the right model within time budget allotted. And many times that model wasn't, it wasn't the best model or the optimal model. And it also wasn't tuned for parameters. So a lot of the deficiencies that she already mentioned, we ran into. And when we adopted FLAML, when we implemented FLAML into our framework, many of those just sort of went away. So we're super excited to be able to use it in our tooling and bring it to the .NET developer community. At that point, you basically just go through your evaluation and consume step. And you also have different options here, right? So one of the really nice things that FLAML sort of gives us is the ability to also inspect our pipeline. So it goes back to that concept of transparency and interpretability. So in this case, what we did here is we generated a notebook. Right? In this case, it's a .NET notebook. You're familiar with Jupyter. Very similar concept here. And within this notebook, what we did is we created the schema of our model inputs and outputs, again, using that data and the training the training configurations that we set in Model Builder. More importantly, though, you'll notice here that we also are able to generate the pipeline. So we're able to inspect what the results of FLAML generated, and we're able to create this pipeline here that not only has the different data transforms, but also the fast tree algorithm that was used to train this particular model, along with all the hyperparameters that AutoML was able to choose for us. So again, this sort of takes away that onus on the developer who from having to figure out what all of these are, and at the very least provide a starting point for developers to sort of train their models. At this point, if one of those developers wanted to go ahead and change this, experiment, try things out, they're more than able to, but at least FLAML provides a starting point, and that starting point tends to be usually pretty good. So with that, I'll kind of pause there, and I'll hand it back to Qi.
Okay, next I will introduce the part about how to do AutoML and tune in FLAML. I'll share my screen. Okay, hello everyone, this is Qingyun Wu. I'm an assistant professor at Penn State University. I'm very glad to be here, and I want to hear your inputs on our work. So in the next 17 minutes also, I will introduce how to use FLAML to perform task-oriented AutoML and to tune user-defined functions. So before I start, I want to mention that we want to hear from you. So we will have a discussion session at the end of this tutorial. Specifically, we want to discuss these two questions and want to hear from you. For example, what challenges did you encounter or do you foresee when using AutoML or trying to use AutoML? And what features do you hope to see in AutoML? Okay, so in FLAML, we have two major APIs, including AutoML and Tune. AutoML is tailored to automate the tuning needed in typical machine learning tasks, and the Tune is an API that allows more flexibility. In FLAML, AutoML is built based on Tune. So let's start from task-oriented AutoML first. In a task-oriented AutoML, given a machine learning task and a particular resource budget, the goal is to find a model with the best performance within the provided resource budget without much manual effort. Here, a task is a machine learning task, including both the training data and a task type. For example, whether you are doing regression or classification and etc. FLAML has a wide range of built-in machine learning tasks you can directly select from. So here is the list of the supported tasks in FLAML. Now, let me use this notebook example to demonstrate how to do a task-oriented AutoML in a very convenient way. So I will, by the way, show you how to find those notebooks I use in this tutorial. So you can directly search for FLAML, and the first one is our GitHub page, and the second one is the documentation website. So for the first notebook, I'm going to see you can find it in the examples, and it is a task-oriented AutoML example for classification task. So I'll use this. Okay, now we can see this notebook. In this notebook, you need to first install FLAML. And here I'm getting a dataset from OpenML. It is a classification dataset. And then after getting this dataset and installing FLAML, I can just create an AutoML instance with FLAML, and then I can just set the input needed to do AutoML. Here we have some additional input which are optional. So in order to show you a most simple example, I will just remove those additional inputs and only keep the minimum ones. So as I mentioned, we only need a task type and a time budget. So let's use this input to run this AutoML task, and I will change this time budget to be 1 minute, such that we can see the result in time. So so we can do AutoML by calling this fit function and providing the dataset and the task type and the time budget to this AutoML instance. And from this console, we can see what are the estimators tried during this AutoML process, and what are the best result we get in real time. Here we can see the loss we get is keep decreasing. Yeah, after getting the after finishing the fitting, we can retrieve the some information you may need from this AutoML instance. For example, what is the best estimator? What is the best configuration? What is the best loss? So now we can see that the best estimator at the 49 second is the GVM, and the best error is 0.297. And you can see what estimators are tried here. You can see we tried XGBoost, CatBoost, and extra tree, and you can also see what are their errors in this training process. Okay. I guess I didn't change this in time. Okay, I think this notebook will keep running, and then we can just see the result we get from previous runs. So by calling this AutoML.best estimator, you can see what are the best estimators, what are the best result and configuration. And then after that, you can directly, you can go ahead and if you need, you can pickle and save the model. And also, of course, you can do prediction based on a particular test data set. For example, I'm doing prediction on this test data set and get the predict the test loss on this data set. And also you can check the log history if you provided a log file name. Okay, now let's go back to the this tutorial. So I have gone through a basic example of task-oriented AutoML. So the benefit of task-oriented AutoML is that we can save manual effort, including both the effort on gluing everything together and the effort on manual repetitive tuning. Second, with the task-oriented AutoML, you can find models with better performance comparing to no tuning and manual tuning. Third, sometimes you can even find models with better performance with less computing resource than that in manual tuning, especially if you are not very experienced in machine learning. But we do know that there are potential concerns about task-oriented AutoML. For example, does one-size-fits-all considering the diverse use case. This concern is also related to one of the major complaints about AutoML on the lack of customizability. Fortunately, in FLAML, we are able to provide rich customization choices while maintaining the performance advantage. Next, I will walk you through some of the most important customization choices that you may find useful. So before going into details, let's first look at the inner workings of FLAML such that you know what are the major components in FLAML and how they are playing a role in the AutoML process and what is the room for customization. So in this AutoML box, the components shown in blue are modules about AutoML, and the components shown in gray are modules about machine learning. Once an AutoML instance receives a machine learning task and the resource budget, it performs multiple trials of tuning and model building within this specified resource budget. Each trial involves one step of estimator selection and hyperparameter selection. It's worth mentioning that in FLAML, we are doing task level and estimator level data pre-processing. So given a particular task, once the estimator is selected, the pre-processing is also determined. So the pre-processing step is not shown in this figure explicitly. Then with the selected estimator and hyperparameter configuration, it trains a model and evaluates the model on the validation dataset and reports the validation loss. The estimator selection and hyperparameter optimization algorithm will be updated with this latest observation, and presumably they can make better decisions in the next trial. For all the components mentioned, we have configured default choices such that most of the time you don't need to worry about them when performing your AutoML task, as shown in the previous notebook example. In that example, you are only providing a task which includes a dataset and a task type and the resource budget. But there, as I mentioned, there can be cases where you do need to revise some of them to satisfy the unique needs in your use case. For example, we know a use case from the security domain where the user wants to use this particular classifier, which is not included in FLAML's AutoML estimator candidates, and she wants to also use a special metric to do the optimization. In this case, she needs to add a custom estimator and customize the loss metric. So let's first look at how to customize the optimization metric. By default, FLAML is using a particular commonly used metric for each task type. For example, it uses ROC, AOC as the metric for binary classification, R2 for regression, and log loss for multi-class classification. There are basically two ways to customize it. The first way is to check this built-in metrics in FLAML. If you find the metric you want to use here, you can directly specify a string to indicate it. For example, if you want to use accuracy as a metric instead of the default ROC, AOC for a classification task, you can just do this. And the second choice is to define to have a user-defined function for the metric function. So this code example shows one example of custom metric. So basically, when you create a custom metric, you need to follow this template, this input and output format. So for the output, it will output two elements. The first element is the optimization metric you are trying to optimize. For example, here we are trying to optimize a weighted combination of the validation loss and the training loss. And the second element is a dictionary of metrics to log. So basically, this is just to log some additional information that you may find useful in the other components. So this part is not necessary. So basically, if you do not have anything to log, you can just pass an empty dictionary. So the next major component you can do customization is the candidate estimator and their corresponding search space. So FLAML has a set of built-in estimators for each task type. Each of them is associated with a default search space. So here are the list of built-in estimators for different learning tasks. For example, for classification, we included LGBM, XBoost, Forest, Extra Tree, CatBoost, logistic regression, and k-nearest neighbor. As you see in the previous notebook example, we can when you do AutoML, you can see from the log which estimators are tried. By default, FLAML will search over all these built-in estimators under each task type, but it's very likely that you want to include only some of them. For example, if your deployment environment only support LGBM and XBoost, you can explicitly tell AutoML to only search for these two types of models by specifying the estimator list to be a list which includes only XBoost and LGBM. If you have an estimator that is not within this estimator list, like in the case we just mentioned, in the use case we just mentioned, you need to add a custom estimator. So let's see how to add a custom estimator. So first, you need to build a custom estimator class by inheriting this base estimator class or a derived class. Here I'm creating an estimator class of RGF classifier which is inherited from sklearn estimator, which is this is a derived class from FLAML space estimator. So in this new class, I'm setting the estimator tab to be RGF classifier or RGF regressor. And I also include a search space, which include the hyperparameters I want to tune on this classifier. After creating this new class, I need to give this class, custom estimator a name, say RGF, and add it to AutoML by calling @learner function. Then I'm ready to use this newly added estimator to do AutoML. So, for example, I can just do the tuning based on only this custom estimator, and or I can also do the tuning together with other estimators, for example, together with XBoost and Lesbian. As you may notice, when creating a custom estimator, it's very likely that you need to add your own search space. So it is important to understand the space, the structure of a search space. A search space of an estimator is a dictionary in which the keys are hyperparameter names. For example, max leaves, number of iterations, learning rate. And each hyperparameter name is associated with a dictionary with the following field. So among these fields, the only required one is the domain. The domain specifies the possible values of the hyperparameter and their distribution. For example, in this specific domain called log_rand_int, it means this specific domain means that I want to randomly sample an integer between this lower limit and the upper limit, and I want to sample in a log scale. So here I'm attaching all the commonly used types of domains. For example, the vanilla uniform sampling within a particular range. Specifically, each of them specifies a type. For example, it is whether it is a numerical type or a float, integer, or a categorical type, and a valid range to sample from. For example, the upper and the lower and upper range. And you can also choose to sample in linear or log scale. So if you need to sample in log scale, you can choose to use log uniform instead of uniform. And I want to mention that it is a common practice to sample in log scale if the valid value range is large and the evaluation function changes more regularly with respect to the log domain. We want to acknowledge that we actually didn't invent all these designs of these domain types. We inherited this design from Retune. So if you are familiar with Retune, you might already know how to interpret it and how to use these domain types. So in addition to the required domain field, there are also two optional fields. The first one is init value. It specifies the initial value of the hyperparameter. The second one is a low-cost init value. It specifies the value of hyperparameter that is associated with a low computation cost. So this concept is meaningful when the hyperparameter is cost-related, which is a key concept in our hyperparameter optimization algorithm. So here I would like to take a detour to talk a little bit about our cost-related hyperparameter and our cost-effective hyperparameter optimization algorithm. So the cost-related hyperparameter are a subset of hyperparameter which directly affect the computation cost incurred in the evaluation of any hyperparameter configuration. They are quite common in ML models. For example, the number of estimator and the number of leaves in gradient boosted trees, the number of layers and neuron in neural network models. This heat map specifically shows the impact of the number of leaves and the number of estimators in XBoost on the cost. So in this heat map, the darker, the more expensive, or the higher cost. It clearly shows that it clearly shows a cost heterogeneity in the hyperparameter space, which indicates that both of these two hyperparameters are cost related. So because of the existence of cost-related hyperparameters, hyperparameter optimization becomes tricky if you also want to reduce the total cost for finding a good hyperparameter. So here we add the word cost frugal in front of HPO to reflect the fact that we also want to minimize the total computation cost while searching for hyperparameter configuration to minimize the validation loss. In this problem, if the cost for different configurations are all the same, then it is sufficient to just minimize the number of iterations for convergence to have a small total cost. But if cost-related hyperparameter exists, we can actually further reduce the cost by trying to avoid the unnecessarily high cost evaluations. Based on this insight, we developed a randomized direct search algorithm, taking the cost heterogeneity into consideration. These two background heat map shows the loss and the cost distribution of configurations regarding the number of leaves and the number of estimators. The black dots are the evaluated points in our algorithm, and the black dot connected by the lines are the points that yield better performance. So this trajectory on these two heat maps shows that we can indeed navigate the points with low loss, and at the same time, we can avoid the high computation cost region. This method is by nature a local search method. In a follow-up work, we further combined this local search method with a global search, such that we do not stuck in a local optimal in case of complex search space. But in both methods, it is very beneficial if we know some hyperparameters are cost related and we know a low cost value for them, especially when the variation of cost is very large. So that's why we have a field called low cost innate value in our search space. In this building estimator, so this is the search space for the LGBM estimator. We have identified and configured the low cost innate value for some of the hyperparameters, for example, the number of estimators, the number of leaves. Now that we have understood the nature or the structure of the search space, let's move on to see how to customize it if needed. So there are basically two ways. The first option is to just create a new estimator with a revised search space, following the steps introduced before. And the second option, which is more convenient if you are just trying to revise the search space of existing estimators, you can just try to override the search space by providing a custom HP as shown in this code example. So in this code example, I'm trying to override some of the hyperparameters search space for XBoost, RF, and LGBM, which are all the built-in estimators in FLAML. More specifically, in this example, I'm changing the domain of the for N estimators to use a different range. So in this example, I used a smaller upper bound for this number of estimators. And in this in the next space, I'm trying to disable the search by just setting the domain to be none. And in the third one, I'm just setting the domain to be a constant value, such that I'm always using this constant value for this hyperparameter named subsample frequency. So another major place you may do customization is the machine learning procedure and ensemble. First, you may want to customize how to transform and organize the data for model training and model validation. For example, do you want to use holdout or cross validation? What is the split ratio and the split type? You can even provide an additional dataset dedicated for model validation purpose via XVal and YVal. If this additional validation dataset is provided, we won't do the data splitting instead of our AutoML process. Second, many people may have their own preferred practice for model training. For example, many people use sample weight in the training process. So if you have such requirements, you can provide your additional input as the keyword arguments to the fit function. Finally, you can also decide whether to do and how to do ensemble after search finished. So far, we have covered the individual components where you can do customization. In the following several slides, I will introduce several customization choices in the whole overall AutoML process. So the next useful customization is about logging. So one of the survey participants in this paper mentioned that comparing to the team who built out the manual process and only able to review 2 or 3 models, he or she is able to look at 50 models and get more insight and understanding on why the model performed the way it did. This comment indicates that the trials and errors produced during AutoML process can be very meaningful information to improve people's understanding on their ML problem. So you may want to log the search trajectory of the AutoML process. And in FLAML, you can easily enable that by just providing a log file name and the way you want to do the logging. So this box in yellow shows one record created during the AutoML process as one of the logs. You can find a very rich information in this log. For example, you can know what is the predict time, the trial time, work clock time, the validation loss, the configuration, and the name of the estimator, and etc. For log tab, if you choose to use all, it will log all the observations created during the AutoML process. And if you choose to use better, we will only log the better observations at any time point. So if you are familiar with MLflow, you can also use MLflow together with FLAML to do the logging. Here I'm setting an experiment with MLflow named FLAML, and then I can run my AutoML experiment in this way. The metrics in this run will be automatically logged in this experiment named FLAML. Then the metrics can be retrieved. Metrics can be retrieved by calling mlflow.searchRuns. In doing so, you can also add a string filter to specify what kind of runs you are looking for. The logged model can also be loaded and used to make predictions. Next, let's take a look at how to impose constraints on different components of the AutoML pipeline. So in summary, you can impose 4 different types of constraints in FLAML, FLAML's AutoML. The first type is a constraint on the whole AutoML process as introduced earlier. Basically, this is a resource budget we mentioned. You can impose this type of constraint via time budget or max iter. So the max iter means the maximum number of iteration allowed. And the second type of constraint is about is on the constructor argument of the estimator. For instance, XGBoost has a constructor argument named monotone constraints, which can be used to constrain its variables. Then we can add a monotone constraint to XGBoost in this way. So basically, we are trying to update the search space because it is a constructor argument. And if you still remember, we introduced a shortcut to revise the search space, which is through the custom HP. You can also do that in this way. Third, you can impose constraints on the models tried in AutoML. Specifically, you can set limit on the training time and the predict time using these 2 keyword arguments. So these two types of constraints are especially helpful in scenarios where due to some business requirement, you need to find models that trains fast or inference fast. Finally, you can add constraints on the metrics of the ML model trained during AutoML, they are the metric constraints argument. You can provide a list of 3 tuples. Like in this example, in each of the 3 tuples, you need to specify first the metric, the name of the metric. Second, the inequality sign. For example, it is whether it is smaller than equal or larger than equal or larger. Third, the threshold for the constraint. In order to impose this type of constraint, you need to provide a custom metric function because we need a metric name. So in the custom metric function, you need to return the metric name you are trying to constrain. For example, because we are trying to constrain the train loss and the vanilla validation loss, you need to ensure that they are reported in this in the second element of the returned object of custom metric. Now let's look at another customization choice about warm start. Specifically, FLAML is able to provide a dictionary of configuration to start with via these starting points. This can be very useful in many scenarios. For example, if according to your past experience, you know a list of good configurations, you may want to incorporate that knowledge into your new AutoML experiment. In this, for example, in this code example, I first did an AutoML experiment with 1 hour time budget, from which I found a configuration with a decent performance. But I want to try if I can find an even better one with a larger time budget, say 2 hours. Since I already got a decent choice from my last experiment, I can just provide them as the starting point of my next AutoML experiment. So the way I do it is basically retrieve the best configuration per estimator from my last experiment, and provide them as the starting point for my next AutoML experiment. So if a large amount of computing resource is available, parallel computing can greatly reduce the workload time of AutoML. In FLAML, doing parallel tuning is fairly easy. And FLAML uses Ray as the parallel tuning backend. To enable Ray parallel tuning, you just need to install Ray and blend search related dependency. Here, blend search is one of our hyperparameter optimization algorithm. It is recommended to use in this parallel tuning scenario. So we need to install blend search related dependencies. And then we can just initialize a Ray instance and Ray backend, and then set the number of concurrent trials accordingly. This easy parallelization feature is actually a very desirable feature according to the feedback we get from users. For example, this company finds a large-scale parallel tuning very helpful in their use case. About parallel tuning, we do have a heads up and suggested practices. First, you need to be aware that when parallel tuning is used, there will be a certain amount of computation overhead in each trial. This can be a problem when the actual time needed to run your experiment, to run each trial of your experiment is relatively small. In this example, I'm doing parallel tuning with 8 concurrent trials. And you can see that from this logged result, you can see that the actual trial time for each of them trial is no more than 0.3 seconds, but the workload time is actually more than 3 seconds. So even if I have 8 concurrent trials running at the same time, the overall workload time is still longer than just running the experiment sequentially without Ray backend. So because of this computation overhead, because of this overhead, we have this following suggested practice. First, when you only have very limited parallel compute resource and each trial can consume all the resource, sequential tuning is recommended. Essentially, when you can consume all your available computation resource with sequential tuning, there is no need to pay the computation overhead needed for parallel tuning. And second, parallel tuning is suggested in the following two cases. First, you have a very large amount of parallel computing resource, and each trial's cost is much higher than the computation overhead caused by parallel tuning. In addition to parallel tuning, in some cases, you may want to enable RAY backends, even if you are doing sequential tuning, because it can help prevent auto-memory failure in case of large data sets. So combining what we discussed in the previous slides, we suggest you to enable RAY backend in these two scenarios. Okay, now that we have gone through some of the most important customization choices in FLAML's AutoML, let's briefly walk through some of the real use cases and the feedback we get. Hopefully, some of them can inspire you about the usage of AutoML in your application scenario. The first one is the use case from the financial industry, where the goal is to find an optimal model that satisfies those business requirements. Those requirements are very well supported by FLAML, for example, via the fast and lightweight hyperparameter optimization algorithm and the support of custom metric. The second use case is from a large private equity firm. This user is trying to find the best model based on business requirements for deployment. FLAML helped to save their dev time, and the high compatibility of FLAML is also appreciated. The third use case is in the domain of custom retention and growth analysis, where the overall objective is to find good XGBoost models. The good performance of FLAML is especially helpful in their use case. The fourth domain is the one we mentioned about from the security domain, which is here the good performance and easy customization of FLAML are especially helpful. Okay, here I would like to pause for a few minutes to have a short question and answer Q&A session. If you have questions, you can enter your question in the chat.
Hi, James. So would you like to answer some questions now?
Excuse me?
Is your plan to answer some questions now? Or later?
Yeah, we can see whether there are questions. If not, maybe we can just
There are lots of questions. Yeah.
Okay.
If you want to answer questions now, I can give you some questions I found from the chat.
Okay. Yes, maybe we can select some of the questions and answer them.
Okay. Let's see. So one question that has not been answered is FLAML integratable with Databricks?
Is FLAML integrated with Databricks?
Integratable with Databricks.
I'm not sure.
Yeah. So,
do you have the answer?
Yeah, I guess we need to know more specifically about the context, like what kind of integration you are thinking of. So, for example, one type of integration is you have some estimator that's specific in Databricks. You could add it as a customized estimator, like Qin just mentioned. Inherit the base estimator class, implement your own fit function. And inside the fit function, you can call some Databricks training routines. That's one kind of integration. So then you can apply FLAML to auto-tune your Databricks machine learners. And another way is perhaps more customizable. That is going to talk about by tuning in the next session for the tune API. So you can implement an arbitrary training function with specific hyperparameters you want to tune at the third space. And so that function inside that function, there's no restriction what you can do. You can run some complex Databricks pipeline, and as long as you return some optimizable metric in the end and specify the hyperparameter search space, you can use that API to do the tuning end to end. So yeah, that are at least two ways I can think of how you integrate with Databricks. If you have other contexts or scenarios that you're thinking of, please specify them in the chat, and we can discuss further.
The other one that I would kind of say also as an integration is more from a logging standpoint, right? So you went over ML flow, right? And ML flow is part of sort of that Databricks suite of products. So even if you were doing training somewhere else, right, at least for your logging and experiment tracking, you can leverage ML flow and Databricks for that.
Yeah, that's a good point. Oh yeah, right. The good one. So when I was talking about Databricks, I was thinking of the Spark kind of the platform. But yes, thanks for reminding me. Yeah, MLflow is also from Databricks, and we already have an integration with that tool. So I don't know. Qing, did you get a chance to demonstrate the MLflow feature?
Yes. A demo. I don't have a demo, but I have code examples in my slides here.
Yeah. We do have a notebook demonstrating
MLflow. Yes.
MLflow.
I think I can find it here.
I think it's integrate Azure ML.
Yeah,
so it demonstrates both how to use MLflow and how to use Azure ML together. You can certainly use MLflow without using Azure ML, and if you use together with Azure ML, then you can also find all the logs available. Yeah, so check that example.
Yes.
Yeah. Okay. That's another question. There's a question from Alpo. The success of machine learning projects heavily depends on quality features generated from training data that's FLAML capable of automatically generating new features. I gave some answer about the data time features we generated in FLAML. Like for data time columns, we will extract some features like year, month, day, week of day, which are commonly used for data time feature generation. And if you have other ideas for other kind of automated feature generation examples, yeah, please also share that in the chat, and we'll see. Maybe it's already handled, maybe it's not. But if it's not, we will see whether it's possible to add that to the library.
There is also a related question about automated feature engineering given a data set for supervised or unsupervised learning.
Yeah, so what's your understanding of the question? Is it the same question or?
Yeah, it's a similar question. In addition to that, we have one related feature, but it is for online learning. In the online learning setting, we are trying to add feature interactions on top of those existing features. But that functionality is currently only for online learning. We haven't extended that to offline supervised or unsupervised learning. But it's potentially possible to add feature interactions, right?
Yeah.
Yeah. Later I'll show you. Yeah. Later I'll show an example of AutoVW, which is trying to add feature interactions. AutoVW.
Yeah.
Here.
Right. Yeah, that's a good example of what you are able to do in the feature engineering space. So because the framework FLAML is so general that you can basically automate a lot of these choices, which are originally not considered as hyperparameters. But if you look at the tuning API, for example, which that's flexible tuning of arbitrary operators you implement, and you could use that also for this purpose, right? If you have a specific, for example, kind of search space for the possible engineering choices, you might be able to encode that as special hyperparameters, right? That specify the choices you want to make in your step. And you can either use the customized estimator in AutoML API or use the tune API for the user-defined function so that you have full control of how you want to implement the feature engineering logic and just ask FLAML to automatically search for good choices for you. So yeah, those are all possible. So we can have some more concrete discussion if you want to be more specific.
Yes, another question is, does FLAML handle high dimensionality by selecting optimal feature or PCA? Currently, we are not doing this, but it is an important direction that we are considering.
Yeah, actually, I think probably in the AutoML.NET and the model builder,
yeah, already doing
that's already integrated. So the pre-processing step can have some hyperparameters, and the pre-processing step together with the training step can be tuned together. There are, for example, for text data, the AutoML.NET has some text data generation and feature selection steps before the training. So that's the example of the high dimensionality, and you need to use some feature selection technique to reduce the dimensionality. For example, the number of dimensions is one that have been correct. So in the model builder and AutoML.NET, that choices can be also automated by FLAML, doing a joint optimization.
Yeah, and that's one part that I didn't really show, but yeah, we recently what I showed earlier was model builder and the tooling, but actually at kind of when you saw that sort of diagram with the platform, there's an API like a code first approach that you have under that, right? Which you're able to use that as well if you need more customization. So a lot of the things that were shown here for task oriented, right? Like the hyperparameter optimizations, the estimator selection, all those things you're able to customize, right? So yeah.
Yeah, thank you. Another question asked is, are there comparison of FLAML against other AutoML or optimization tools? So in the paper, we reported a comparison with some of the service providers and some AutoML tools. In this paper, you can find it in this paper. Yeah. And I think we are also integrated. FLAML is also integrated into the AutoML benchmark, which is a benchmark regularly compared like different AutoML tools, and they will report the results like quarterly, I think, and if you can check there. Okay, I think we are like ready to start the next session. Maybe we can continue the question answering after the next session.
Yeah. Also, I think some of the questions will become clear once we introduce the tuning API, which is another very powerful API in FLAML.
Yes.
Oh, sorry. Yeah, my microphone was lifted up, so I wasn't sure whether people can hear.
Volume is a little bit low, but now it's good.
Oh, okay. Sorry about that.
Okay, sure. Maybe we can continue our tutorial. Okay, before I start, let's first look at the notebook I run. So basically, at that time, I was trying to run it for 1 minute, but I wasn't able to change that in time. So basically, the notebook runs for 10 minutes, and then we got the 10 minutes result now, and we can see the best model we find is a cat-boost model, and then you can try to see what are the, for example, the best result, the best configuration, and the best model. Now it's a cat-boost model, and then you can do the follow-up steps to investigate the results. Okay, now let's go back to the tutorial. Okay, so next I'll introduce how to use FLAML to tune user-defined function. So before zooming into the details, let me first clarify when you should use AutoML and when you should use tune. From the workflow of AutoML and tune, you can see that in order to use AutoML, you need to frame your machine learning task into a sklearn fashion, which consists of a model training process and a model fitting process. And a model inference, and you need to have a validation data set to get the loss. But there are cases where the optimization metric cannot be implemented into such a custom metric function, or even if you could, the engineering cost could be high. In such cases, it is more convenient if you can write a user-defined function to cover whatever procedures you want to include in your configuration evaluation process. For example, when the evaluation regarding the optimization metric relies on some downstream applications and the data that cannot be collected upfront, which are pretty common in the context of MLOps. And sometimes some hyperparameters are even not about the training models, but about how to use the model. One use case we know is a scenario where the user is tuning hyperparameters to find the best bidding strategy based on ML models that predict the prediction or the probability of a comeback in a basketball game. With tune, you can easily include whatever needed, for example, the downstream applications into this user-defined function to achieve your goal. Next, let me use a toy example to show you how to set up a basic tuning procedure with tune. The first thing you need to do is to have a search space. What are the variables you want to tune? What are the search range, and how you want to sample them? The structure of the search space in tune is a little bit different from that in AutoML. In tune, the search space is just a dictionary with the keys being the names of the hyperparameter you want to tune, and the values are the domain of the hyperparameter. The format of this domain is the same with the one introduced in AutoML. So it's still this list. The second thing you need to do is to define you have this user-defined function, which consists of an evaluation function, an optimization metric, and an optimization mode. The evaluation function takes a hyperparameter configuration as the input and output a dictionary of results. The returned dictionary should at least include your optimization metric and some additional metrics you want to log. You can either return this dictionary or use tune.report to report it. Finally, you can specify one or more resource constraints, which can be used as a stopping criteria in the tuning process. For example, how long or how many iterations you want the tuning process to run. With those three basic elements, you can set up your tuning procedure in this way. You need to first call this tune.run function and provide the search space, the tuning objective, including an evaluation function, the optimization metric, and the optimization mode. And finally, a resource constraint in terms of the time budget and the number of samples you want to run. After finishing the tuning, you can also retrieve the best results and other information you want to know, such as all the results, the best configuration, and etc. from this returned analysis object. Now I want to use this notebook example to show you an example of how to use tune to tune hyperparameters in PyTorch. So again, you can find this example on this documentation set. And because this example will takes time, I will not run this live example, just to show you how to set up this tuning procedure. So basically, you need here is the place where we launch the tuning. Here we are calling the tune.run function, and we provide the hyperparameter search space. Here, the name keyword argument is config, and if you look at the config, this is the hyperparameters we want to tune for the PyTorch model. And the next one is the evaluation function. So basically, we are using this train cfar function as the evaluation function. So basically, this is the place where we set the evaluation function. So basically, in this function, we train a PyTorch model and get the validation loss. And finally, we report the validation loss and also the accuracy. And you may notice that there are some additional inputs, for example, the max resource, mean resource scheduler. So those are all optional ones for intended for more advanced tuning. So if you do not need them, you can just remove them and run a simple example. And I will introduce those more advanced tuning options in my next few slides. Okay, so the benefits of tune is to first save human effort on repetitive tuning, and the second and third benefits are in terms of efficiency and effectiveness. So those benefits are also the benefits of AutoML, and in addition, tune has additional benefit of in terms of flexibility. It supports even more diverse use cases than AutoML. So with a basic understanding on the basic tuning procedure, let's now look at some features related to search space that can make your tuning even more efficient. First, let's see how to accommodate the cost-related hyperparameters in tune. As we mentioned, those cost-related hyperparameters are mentioned in previous slides. So the first relevant keyword argument is the low-cost partial config. It can be used to specify the controlled dimensions where we know the value-cost value. For example, when we are tuning like GBM learner, we know a configuration. With small value of number of estimators and max leaves correspond to a model with low cost. Then we can provide this information to tune via the low-cost partial config. If you still remember, in AutoML, we are taking this information into consideration via the low-cost init value in the search space. The second relevant keyword argument is cat HP cost. It can be used to specify the relative cost across different categorical choices, if such information is available. For example, according to my past experience with LightGBM, I learned that the relative computation cost and the different LightGBM model with different booster tab of GBDT goals start are 2 to 3 to 6. Then I can provide this additional information to cat HP cost. This additional information about search space is uniquely leveraged by FLAML's hyperparameter optimization algorithm to make the search more efficient. And of course, if you do not have such knowledge, you can always omit them. Another desirable feature about our search space in FLAML is the support of hierarchical search space. It can make your tuning process very convenient if a hierarchical search space indeed exists. For example, in XGBoost, depending on the type of booster, you have very different groups of hyperparameters. More specifically, in the case of GB tree, you have these are some of the hyperparameters you need to tune. And in the case of GB linear, the hyperparameters you need to tune are totally different from the case in GB tree. So with tune in FLAML, I can directly code the search space in this hierarchical way and then directly do the tuning as shown in this code example. So here I'm providing this hierarchical search space to as a search space in the tuning process, and then write the objective function accordingly. Then I can just do the tuning at one time. Since we are talking about search space, I want to mention again the two hyperparameter optimization algorithms used in FLAML. In AutoML, we have made a decision about which one to use, but in Tune you can make this decision yourself. Based on the nature of these two hyperparameter optimization algorithms, we suggest you to use CFO when your search space is simple, and there are low-cost good starting points. And you are also not doing parallel tuning, or the parallelization is low. Otherwise, we suggest you to use blend search because it is more robust. And in order to use CFO or blend search, you can just specify the search algorithm when calling the tune.run function. And when you want to use blend search, you need to install the blend search related dependencies. Another important feature of Tune is the capability to accept various of constraints. This actually directly contributes to AutoML's customizability on the constraints introduced before. In addition to the resource budget on the tuning process, you can specify these following two types of constraints. The first type is the constraint on the configuration itself. For example, for some reason, if you want to ensure the product of these two configuration, weight and height, then you can just write a function to reflect your requirement and then add a config constraint in this way, which is a list of 3 tuples. And the first element of this 3 tuple is the function in terms of the configuration, and the second element is an inequality sign, and the third element is a threshold. And you can also add a metric constraint via this metric constraints argument. If you still remember, in AutoML, you can also do this. And here the required format and the motivation for adding a metric constraint is the same. So I will omit it here. You can also enable parallel tuning in Tune as well, which actually enables the parallel tuning option in AutoML. When using AutoML, some of the parallelization details are hidden in the AutoML layer, but when using Tune, we need to expose those details. So after installing those related dependencies, including the required array related dependency and the recommended blend search hyperparameter optimization algorithm, then you need to set use rate to true and also specify the hardware resources to allocate per trial. For example, the number of CPU cores. Finally, we want to highlight that FLAML.tune offers a unified API for both single process and multi-process tuning. So another unique feature of Tune is the capability to support warm start. This is also related to the warm start feature in AutoML. So basically, there are 2 keyword arguments related to warm start. One is called a point to evaluate. It takes a list of initial configuration to start first, and another related argument is evaluated reward. It is a list of reward for the corresponding configurations provided in points to evaluate. Here, I would like to include a closed issue on GitHub to show the motivation of this warm start feature and how these 2 keyword arguments are helping. First, this user would like to leverage results from previous runs. And second, in addition to the previous results from previous run, he is also trying to add some new points to evaluate first. These two demands can actually be well satisfied with the help of these two keyword arguments. I'll use this toy example to show how to do it. In this example, say the two hyperparameters to tune are A and B, and I have two configurations that I have evaluated and know the reward. Say the first two hyperparameter configurations, then I can just pass them to points to evaluate and the evaluated reward. And if I have additional points to evaluate, I can just append them at the end of this points to evaluate list. So the configurations in green are evaluated configurations and their results, and the configurations in blue are the additional points to evaluate. And after setting these points to evaluate and evaluated the reward in this way, I can just provide them to my tuning process in this way. And this screenshot is a log of this tuning process. And from the log, we can see that the additional points to evaluate are indeed evaluated first. Another important feature in Tune is that you can enable a scheduler to help manage your trials. For example, to do some early stopping. In a nutshell, a scheduler is an algorithm which helps manage the trial's execution. It can be used to perform multi-fidelity evaluation and perform early stopping. The related keyword arguments in Tune include the following ones. First, you need to specify a scheduler. We have two built-in schedulers, including FLAML, which is an authentic scheduler in FLAML, and ASHA, which is a synchronized successive halving algorithm. And you can also specify a user-defined instance of this trial scheduler class from Retune. When you use a scheduler, there must be a resource dimension. With a resource dimension, you can do multi-fidelity evaluation. For example, sample size can be considered as a resource dimension. And when you use a smaller sample size, you are actually doing a lower fidelity evaluation. And when you use a full sample size to do the training, you are getting a highest fidelity evaluation. And the mean resource, max resource, and the reduction factor are also needed to control how you change the resource. So here, let me briefly show you how the FLAML scheduler works and how these resource-related concepts play a role in this scheduler. So inside the FLAML scheduler, there are two dimensions of choices. The first, in this axis, I denote the choice of hyperparameter configurations. So this is the search trajectory in FLAML. And the y-axis is the resource scheduling. So once the mean and max resource value is specified, we have a lower and upper limit of the resource we can use. And then with the reduction factor, we'll have a geometric resource schedule. For example, if 2 is used, the schedule looks like this. And then FLAML scheduler starts the search with the minimum resource. For example, because the minimum resource is R, so we start the search with the first, the initial configuration C0 and with the minimum resource R. And at any time point before the maximum resource is reached, say at a current configuration of CI and with resource 2R, it makes a decision between the choice of trying a new configuration with the current resource, and trying the same configuration with a higher resource value. This choice is made based on which of the option leads to a faster improvement of performance. For example, if the algorithm finds that we can keep making improvement with the current resource, we actually do not need to increase the resource. So we will move to this point, this in green, in blue. So if we keep doing so, it's very likely that we can do the search under a particular low resource budget and only increase the resource when necessary. So this overall can save us a lot of resource in total. So these three figures show the performance of our search algorithm in FLAML with and without the FLAML scheduler. So here, a sample size is used as a resource dimension. So when FLAML scheduler is not used, the method is named food data. So this is one with or without FLAML scheduler. So from all these three results, we can observe that if FLAML scheduler is used, we can save a lot of the computation needed for AutoML. So basically, we can achieve better results within the same resource budget. Now let's see how to use the FLAML in Tune. So the first important thing is to identify a resource budget based on how to do multimodality evaluation. For example, here the data sample size is used as a resource attribute, as a resource dimension. And then you need to specify the mean resource, max resource, and the reduction factor. Here I'm using mean resource of 1,000 data sample. And the next critical step is to realize this multimodality evaluation in your evaluation function. So when writing this evaluation function, one thing you need to know is that when FLAML scheduler is used, the suggested configuration contains the additional resource dimension. So you can directly get the current resource value from this configuration variable, even though the original hyperparameter search space it does not contain this resource dimension. And then after getting this resource value, you need to know how to use this resource to do multimodality evaluation. For example, when sample size is used as the resource dimension, we can do multimodality evaluation by training a model using a subset of the data. And this is the way to write this evaluation function when the FLAML scheduler is used. When you use the Asha scheduler or a user-defined scheduler, the objective needs to be written in a slightly different way to do the multimodality evaluation. Due to the time limit, I will not include it here, but you can find it in our documentation set. Okay, now let's go back to the use case about Tune, in which the user is trying to find a good bidding strategy based on ML models that predict the probability of a comeback in a basketball game. In this use case, each evaluation involves a simulation with a certain amount of bootstrapped samples. The scheduler in Tune can also help do this resource allocation and do early stopping by treating the bootstrap samples as the resource attribute. Now we have covered most of the the essential steps for tuning a user-defined function and the several important features of the Tune function. Now let's do a brief recap. Here we have introduced the two major APIs in FLAML, including AutoML and the Tune. The AutoML class has a lot of built-in stuff for machine learning tasks. For example, data splitting, commonly used metrics. So if you are facing a well-formulated ML task and the models can be evaluated with the validation dataset, you should consider using the AutoML API. Otherwise, you can use Tune. Since AutoML is built on top of Tune, both of them are fast and lightweight because of our efficient hyperparameter optimization algorithm. Finally, I would like to share a user feedback from AutoCausality, which is an open source library for automated causal inference models estimation and selection. It is using FLAML's AutoML API to do generic regression and classification tasks, and using the Tune API to do estimator and hyperparameter selection on causal models. This is a very typical example where these two APIs can be very helpful. So far, we have gone through some of the essential steps to do task-oriented AutoML and the user-defined function. If you are interested in knowing some more details about them, please check out our GitHub page and documentation set, where you can find the dedicated pages for these two use cases and more information. For example, examples and how to contribute. In addition, you can also find a frequently asked questions session in the documentation set. here, and in this page, it includes some detailed explanations on some of the frequently asked questions. For example, questions about the low-cost partial config, imbalanced data, and the model performance interpretation. Okay, I'll pause for another 10 minutes to answer questions.
Thanks, Jean. There are some questions from the chat.
Okay.
Yeah, let me. So the first question is, why do we need scheduler? It's from Samira. So the question is about the scheduler part.
Mm-hmm.
Yeah, why do we need a scheduler?
Why do we need a scheduler? So first of all, this is not required. Like you only need to use it when you have such need. So the reason why you want to use a scheduler is sometimes you can do multi-fidelity evaluation, and the multi-fidelity evaluation allows you to do some early stopping. And you can imagine that if early stopping is possible, you can save a lot of resource on trying those bad configurations, and then you can spend more resource on those more promising on the more promising ones. Maybe we can use this example, from this use case. So in this use case, a full fidelity. So in this use case, the multi-fidelity evaluation is can be conducted by using different bootstrapped sample. Like if you do not have a multi-fidelity evaluation, you need to do the bootstrapped sample on a full data sample size. For example, this user mentioned the full sample size is 1,000, and it takes time, right? For example, it takes 1 hour to finish this bootstrapped sample on one configuration. And if you want to try 1,000 configuration, then it is 1,000 hour, right? That is very large. But if you can try a experiment with a lower sample size, for example, 30 samples, then the cost is much lower. And with these 30 samples, you can still get a result. This result can be used as a proxy for the ground truth result. And this proxy result can help you, for example, eliminate some bad results. And then you can spend more resource on the good ones. Yeah, hope this answered the question.
Yeah, I also add that in the AutoML API, for example, it also leverages this scheduler capability to handle the sample size of the data set cleverly. So, for example, it will begin with some small sample size of the trained data set. If the trained data is large, then training even one model on the full data set will be very expensive. It will take a long time to even get your first model.
Yeah.
So FLAML leverages that scheduler to start from small sample size and gradually increase the sample size, eventually to use the full sample size. But because the best hyperparameters for different sample sizes are also different, so we need to know like when to change the hyperparameters and when to change the sample size. So that's what the FLAML scheduler does. And we've seen that with and without that scheduler, the AutoML performance has a big difference in terms of the performance curve. So with the scheduler, the optimization performance it converges much more quickly than without the scheduler.
Yes.
And yeah, so if you use AutoML, then you don't need to worry about this detail. It's already used internally by the AutoML API, so you don't need to see that detail. But if you use the Tune API, then this is some feature that we want you to know, so that if your application does allow this multi-fidelity evaluation, you might want to consider this to speed up your tuning job. Yeah. So let's go to the next question.
Okay.
So from Chris Ruff, Great talk so far. Can you briefly comment on the performance of Blend search versus, say, the default TPE search using Optuna or HyperOpt? Also confirm that Blend search works with hierarchical parameters.
TPE in Optuna?
Yeah.
I think we have the comparison in the Blend search paper.
Are you going to explain it?
Yeah, I'm trying to find the paper. Yes, we did the comparison with Bayesian optimization method, and actually, Blend search is combining the local search from FLAML with the global search method from Optuna. So basically, it is trying to leverage. Yeah, the short answer is Blend search performs better, but I want to explain that we did perform comparison with this, and actually we are trying to Blend search is trying to combine the advantage of local search method and the global search method in Optuna. Any other questions?
And could you also confirm that Blend search work with hierarchical parameters? Yes, I can confirm that.
Yeah. Mm-hmm. Thank you.
Maybe we can mention the question earlier asked because I think it's related to the example you mentioned.
Sure.
So there was a question about there was a question from Levi. Have users used FLAML as an advanced A/B testing framework? That is, use FLAML generated hypothesis in production instead of offline. That would make sense in settings where the model affects the environment and offline evaluation would not reflect distribution shifts.
Have user used autocausality is using FLAML to do A/B test, but I'm not sure whether they used in, for example, some real product to do the follow-up verification. Right?
Yeah, so according to my knowledge, it's used by Wise. It's a
Yes.
company in the finance industry. Yes, they have been applying FLAML and causal inference libraries in their production workload for the CRM application. And that was used for some advanced A/B testing. So yeah, because exactly the problem is exactly that when you only have the offline data, sometimes it's hard to know the true effect of having a feature or not in the product. But using the causal inference framework, you can do this without collecting too many expensive samples. And FLAML, as Qingyun mentioned in his presentation, FLAML is used in 2 ways. So they use FLAML twice. Once is in the regression, whenever you need a machine learning predictor for regression or classification purpose, you can just use FLAML there using the AutoML API. And on the other hand, for the causal inference part, that's some new estimators users want to tune for their customized need. They use the tune API to do the tuning for that part. So we see some organic way and very creative way of using both APIs in one applications. So this also demonstrates somehow like when you should consider using the AutoML API and when you could use the tune API, and to expand the scope of the tuning you want to do, all the automation you want to make. Yeah, especially when you use a machine learning model in downstream application where you have multiple steps and some complex evaluation, for example, or even some online evaluation. The tuning API can help you do this end-to-end tuning somehow. Yeah. So how are we on time? Do you want to answer one more question, or shall we move forward?
Let me see the schedule. Yeah, I think we can move forward.
Okay. Yeah, I think all the questions in the chat have been answered so far. Please double check when I talk about the next section.
Okay,
if we missed any question, we can answer them later. Yeah, in the end.
Sure. Yeah,
also,
we'll have a discussion session at the end, so we can answer more questions there.
Yeah, that's also something I want to reiterate. We really want to hear from the audience about some unique challenges you face in your workload, and and your suggestions about, for example, new features to add in the tool. So please type them anytime you want to. You don't have to wait until the end to make your suggestions. You can do that in the middle, but we will collect them in the end and have some more thorough discussion.
Yes.
Yeah. So with that, let me share. Okay. Cool. Yeah. So we have finished the first half of the workshop. So in the following, I will talk about some new features in FLAML, zero-shot AutoML, and time series forecasting. I'll spend 20 minutes in zero-shot AutoML. So what is zero-shot AutoML? It means AutoML system without expensive tuning. And this is a brand new way of approaching AutoML. Let me explain it. Think about what happens when you use a LGBM regressor. When you initialize a LGBM regressor without any argument, it will set all the hyperparameters to the default values preset by the LGBM library. Okay, there's no doubt that these default values have been carefully chosen by the library developers, but they are static. They're not adaptive to the different datasets. No, it's hard to believe that 100 trees and with 31 leaves each is the best hyperparameter setting for every dataset. So we propose to recommend data-dependent default configurations and runtime. All you need to do is to import the LGBM regressor from flaml.default instead of from LGBM. So other parts of the code remains the same. The new LGBM regressor will automatically choose a configuration according to the training data. For different training data, the configuration could be different. The recommended configuration can be either the same as a static default configuration from the library or different. It is expected to be no worse than the static default configuration in most cases. We have a notebook example here. You can try that by yourself. But I will go over some of the details here. So for example, when we fit the regressor on the house price prediction tasks from OpenML, the configuration is adapted as shown here. The number of trees is, let me use some marker. So the number of trees is 4797. The number of leaves is 122. Does it work better than the static default configuration? Let's compare. When using the LightGBM regressor with the static default configuration, the R-square metric is 0.8296. When using the LGBM regressor with the data-dependent configuration, the R-square metric is 0.8537, much better. Again, the only difference is in the code is from where you import the LGBM regressor. So that's the only difference. The adaptation to the training dataset is under the hood. You might wonder, how is it possible to find the data-dependent configuration without tuning? If tuning is not really required, why did we spend so much time talking about tuning in the first half of the tutorial? The answer is that FLAML can recommend good data-dependent default configurations at runtime without tuning, only because it mines the hyperparameter configurations across different datasets offline as a preparation step. So basically, zero-shot AutoML shifts the tuning cost from online to offline. All the previous tuning techniques we talked about are still applied in the offline preparation stage. So now, what's the benefit of zero-shot AutoML? Or what's the benefit of shifting tuning from online to offline? The first benefit is the online computational cost. So that's the cost paid by the final consumers of AutoML. So they only need to train one model. They get to the hyperparameter configuration right away. There's no overhead to worry about. Another big benefit is that your code doesn't need to change. So if you currently have a workflow without a step for tuning, you can use zero-shot AutoML without breaking that workflow. So compared to tuning-based AutoML, zero-shot AutoML requires less input. For example, it doesn't need a tuning budget. Yeah, by the way, which is also a question asked by some users in the chat. And I have some answer in the chat, but here's another answer. So if you really don't know how to set that, you could try the zero-shot feature. And the related benefit is that you don't need to worry about holding a subset of the training data for validation, which the tuning process might overfit. And as there's no tuning, you can use all the training data to train your model. No need to worry about resampling strategy or data split, etc. And finally, you can customize the offline preparation for a domain and leverage the past tuning experience for better adaptation to similar tasks. The easiest way to leverage this technique is to import a FLAMLized learner of your favorite choice and use it just as how you use the learner before. The automation is done behind the scene. The current list of FLAMLized learners are these. They work for classification or regression tasks. So what's the magic behind the scene? FLAML.default LightGBM regressor inherits LightGBM.LightGBM regressor. So all the methods and attributes in LightGBM.LightGBM regressor are still valid in FLAML.default.LGBM regressor. The difference is FLAML.default.LGBM regressor decides the hyperparameter configurations based on the training data. It would use a different configuration if it's predicted to outperform the original data-independent default. If you inspect the parameters of the fitted estimator, you can find what configuration is used. If the original default configuration is used, then it's equivalent to the original estimator. The recommendation of which configuration should be used is based on offline AutoML run results, and information about the training dataset, such as the size of the dataset, will be used to recommend a data-dependent configuration. The recommendation is done instantly in negligible time. The training can be faster or slower than using the original default configuration, depending on the recommended configuration. Can I check the configuration before training? Yes, you can use this method to find the suggested configuration. For example, when you run this code with the houses dataset, it will return the hyperparameter configuration instantly without training the model. You can print the configuration as a dictionary in case you want to check it before you use it for training. This brings up an equivalent open box way for zero-shot AutoML, if you'd like to have more control over the training. Import the function pre-process and suggest hyperparameters from FLAML.default. This function takes the task name, the training dataset, the estimator name as input. It outputs the hyperparameter configurations, estimator class, transformer data, feature transformer, and label transformer. In this case, the estimator name is LGBM. The corresponding estimator class is LGBM.LGBM regressor. This line initialize the LGBM regressor with the recommended hyperparameter configuration. Then we can fit the model based on the transformed data. The feature transformer is also returned, and it needs to be applied to the test data before prediction. These are automated when you use a FLAMLized learner, so you don't need to worry about these details when you don't need to open the box. We demonstrate them here to help you understand what's going on, and in case you need to modify some steps, you know what to do. Zero-shot AutoML is fast and simple to use. It's very useful if speed and simplicity are the primary concerns. If you are not satisfied with the accuracy of the zero-shot model, you may want to spend extra time to tune the model. You can use flaml.automl.fit to do that. Everything is the same as before, except to set starting points to be data. That's here. This tells AutoML to start the tuning from the data-dependent default configurations. You can set the tuning budget in the same way as before. And note that if you set max iteration as 0 and time budget as none, you are effectively using zero-shot AutoML. When estimator list is omitted, the most promising estimator together with its hyperparameter configuration will be tried first, which are both decided by zero-shot AutoML. The key idea of zero-shot AutoML is that instead of running full hyperparameter tuning from scratch every time, one can leverage the tuning experiences in similar tasks before. While we have offered the meta-learned defaults from tuning experiences of several popular learners on benchmark datasets for classification and regression, you can customize the defaults for your own tasks /learners/metrics based on your own tuning experiences. This customization ability is intended for those who would like to build their own meta-learned defaults. For example, AutoML providers for a particular domain, or data scientists or engineers who need to repeatedly train models for similar tasks with varying training data. The meta-learning approach in FLAML is demonstrated in this picture. The input to meta-learning contains several things: a set of tasks and their meta-features, a set of hyperparameter configurations, and the results on each input task. The output of meta-learning is a portfolio of hyperparameter configurations and the decision function that maps a feature-wise task to a configuration. Let's go over these concepts one by one. First, we need to collect the diverse set of training tasks. For each task, extract its meta features and save in a CSV file. For example, this test default/all/meta-features.csv. The first column is the dataset name, and the latter four are meta features. Each training task is described by 4 meta features: number of instances, number of features, number of classes, and percentage of numeric features. And next, we need to prepare the candidate configurations. We can extract the best configurations for each task in our collection of training tasks by running FLAML on each of them with a long enough budget, and save the best configuration in the JSON file. And that gives us one candidate configuration. If you do this for every task, you will have a set of candidate configurations. You can also use multiple configurations per dataset. Next, we need to evaluate each candidate configurations on each task. The save evaluation results in the CSV file. For example, save the evaluation results for LiveGBM under test default LiveGBM results.csv. The type column indicates the type of the task, such as regression, binary, or multiclass. The result column stores the evaluation result, assumed the larger the better. The params column indicates which JSON config is used. For example, LGBM/2dplanes.json indicates that the best LGBM configuration extracted from 2D planes is used. And different types of tasks can appear in the same file as long as each JSON config file can be used in all the tasks. For example, LGBM slash 2D planes.json is extracted from a regression task, and it can be applied to binary and multi-class tasks as well. Based on these inputs, FLAML will build a portfolio of good configurations. Here's an example of the portfolio. It contains 2 configurations for random forest. The first configuration sets number of estimators to be 1907, max features to be 0.37, max leaves to 11,731, and criterion to entropy. The second configuration is the static default configuration. A portfolio can contain configuration for different learners. FLAML will also learn a decision function based on the inputs. The decision function maps a task to a configuration. We featureize each task by meta features. The meta features are fast to compute. We use the nearest neighbor classifier to find the nearest neighbor task in our training task set. Then we follow the preference order of that nearest neighbor task over the configurations in the portfolio. For example, if the first task is the nearest neighbor task over the configurations in the portfolio, we will find that in the first configuration. To recommend should be choice 0, and which corresponds to the first configuration in our portfolio. With this approach, we can recommend multiple configurations in the sorted order. So you can easily extend our zero-shot approach to k-shot. To recap, the inputs required for meta-learning are meta features, configurations, evaluation results. For example, if the input location is mine, learners are LGBM and RF, random forest, the following command will learn data-dependent defaults for binary classification tasks. In a few seconds, it will produce the following files as output: my/lgbm/binary.json containing the learned defaults for LGBM, rf/binary.json for the learned defaults for RF, and all/binary.json containing the learned defaults for LGBM and RF together. These JSON files contain both the portfolios and the decision functions. To update the learned defaults when more experiences are available, simply update your input files and rerun the learning command. After generating these files, you're ready to use your own meta-learning defaults. Just specify the path containing the JSON files. In each of the 3 ways of using zero-shot AutoML we've introduced, there's the optional argument to specify the location. Let's look at the last example. It's a multi-class task. AutoML will look for the following files under location for defaults. One file is all/multiclass.json. It contains the meta-learning results for all the estimators. The other files are like learner name/multiclass.json for every learner name in the estimator list. So you have now effectively built your own zero-shot AutoML solution. Congratulations. And now you have the option to FLAMLize learner using flaml.default.flamlize estimator for easy dissemination. For example, here's how we FLAMLize the extra trees classifier from scikit-learn after we run meta-learning for this classifier. Then you can share this FLAMLize extra trees classifier together with the location of your learned defaults with others, and they will benefit from your past experience. Your group can also share experiences in a central place and update the learned defaults continuously. Over time, your organization gets better collectively. If you'd like to understand more details about our meta-learning approach, please refer to this paper. We wrote about our new algorithm to build a robust portfolio efficiently, and we presented an extensive empirical study in this paper. Here I can briefly talk about some interesting results. As an application of our technique, we study whether the recommended zero-shot configuration is better than the library default for popular and mature learners such as LightGBM, XGBoost, and Random Forest. Each learner has offered the default configuration, which is supposed to be robust across tasks, as they have been adjusted by the library maintainers through many iterations of development cycles. These learners are widely used and testified by data scientists for many applications and evolved for many years. So with such a high degree of maturity and a huge amount of crowd wisdom already built in, chances low for there to be a universally better default configuration. However, it's an intriguing question on whether we can recommend data-dependent default configuration, which is equal or better than the library default consistently. It would not be surprising for this to be true in some tasks, but it's a tall order for an automatic zero-shot approach to outperform the carefully crafted default for every task. This figure plots the tenfold cross-validated R-squared score. The larger the better. And for LightGBM on 37 regression tasks, the light blue bar is from FLAML and the dark blue bar is from LightGBM. We observe that the recommended zero-shot configuration consistently outperforms or equalizes the static default configuration. The margin is large in quite a few tasks, such as BNG, Libra Smooth, with more than 20%, 24%, like New York Taxi, Yolanda with 15 and 17%. The static default from LightGBM performs catastrophically in some tasks like the Brazil houses with a negative R-squared score versus 0.76, and the poker 0.28 versus 0.94. The zero-shot approach stands strong in the worst-case performance. The only case where the recommended zero-shot is worse than the static default is on the task commit, where the R-squared scores are within a 0.5% margin. So overall, the portfolio demonstrates a robust performance against diverse tasks and looks promising and strong as a strong alternative to static preset. We applied the same study to XGBoost, Random Forest, and extra trees and observed the same. And we have shared the mine portfolios and decision functions in our GitHub repo. So maybe let's quickly answer some questions for this zero shot before I move on. Does zero shot always give better results than the default model? I mean to say, has there been a statistical significance being established for zero shot results being better? Yeah, as I mentioned in this experiment, it's consistently outperforms or equalizes in most cases, but also there's no guarantee it's true for every task. But we see that in most cases it's either better or very close to the static default in our empirical study on a very large set of diverse tasks, and you can find more evaluations results in the paper. The question from Rini Zhang: noticed in the market, LightGBM is popularly used. Does it outperform better than all the rest algorithms? No, not always. So LightGBM is indeed a very popular library, and it's indeed a winner in many cases. But still, given the diversity of all the possible tasks, there are cases where other libraries are better, and that's why we need to include these different learners in the search space when we are not sure about the best learner. Yeah, and another question from Rini: can the ensemble models do better? It depends. Yeah, I think I will talk about the ensemble in the discussion part in more depth. But the quick answer is, it depends. Like some cases ensemble better, some cases single random is better in terms of accuracy. And also, if you look at other metrics beyond accuracy, such as like inference time, right? Then the single model usually wins. And also, for example, explainability or debuggability or robustness wise, yeah, in terms of these metrics, then single model often has advantage. Ensemble, but one advantage of ensemble is usually it has better generalizations. For example, when your data distribution changes, the ensemble can have some advantage in terms of robustness over different time because of the diversity of the models contained in the ensemble. So yeah, so it's really not a universal answer like whether ensemble is better. It depends on your specific task. Okay, let's move on, and we can have more discussions in the discussion section for more questions. So now I will switch gear and introduce the time series forecasting in the next 10 minutes. The time series forecasting tasks are special classification or regression tasks. The forecast label can be either numerical or categorical, corresponding to regression or classification. So numerical labels are most common for time series forecasting, such as sales and price. By default, if you specify the task as TS forecast, it assumes the labels are numerical. If you want to be explicit, you can use TS forecast regression as a task name. Categorical labels are not very common for the time series forecasting scenario, but you can set the task as TS forecast classification for such cases. So what's the difference from standard classification or regression tasks? First, the data are ordered by a column with the data time type. The time points have equal intervals like daily, weekly, or monthly. The same interval will be used for forecasting future data. For example, if the time points have daily intervals, then we can forecast for 5 days from now on, 10 days from now on, 20 days from now on, and so on. If the time points have monthly interval, then we can forecast for 3 months from now on, 6 months from now, and so forth. The number of future time points to predict is the forecast horizon. The forecast horizon needs to be specified when training the model. In other words, the number of predictions to make is bounded and known when training the model. So that's the second difference from normal regression or classification tasks. Because of the two special properties of time series forecasting tasks, there are a few things we need to pay attention when preparing the dataset. Here we show one example of time series forecasting dataset that can cover a generic use case. The task is to predict the sales volume of soda for a store in each month, and different SKUs correspond to different soda products being sold. For simplicity, let's assume there are 2 SKUs, so the dataset contains 2 time series to forecast. The date column contains monthly timestamps. The volume column is the forecast label. The forecast horizon can be, for example, 3 months, so that the store can arrange its plan accordingly. The first 3 columns are pretty easy to understand. What about the latter 3? Month is a categorical feature that changes over time. Price and temperature are numerical features that also change over time. Price means the regular average price at each month, which has been predetermined as the forecasting time. Temperature means the average maximal temperature in each month. There's a fundamental difference between price and temperature. In this case, price is known for a future date, but temperature is not. Why is this important? Remember that we need to make the forecast in advance before we observe the actual temperature. So even though the temperature column is available for the dates in the training data, it's not available in the forecasting period. The model needs to be aware of that. Not every type of columns is necessary to appear in the dataset. A minimal valid valid dataset needs to have two columns, the timestamp column and the forecast label. The ID columns and feature columns are optional. If there's no time series ID column, then the timestamps must be distinct. There can be multiple ID columns, for example, skill and store. Each unique combination of the categorical values from the ID columns determines a separate time series. FLAML supports three categories of estimators. Traditional statistical models like Profit, ARIMA, and Cerimax are specialized for time series forecasting. They are designed for forecasting a single time series, so they don't allow ID columns. Regressors or classifiers like GBM and XGBoost can be used for time series forecasting with appropriate feature engineering. FLAML supports these estimators and performs automatic feature engineering for them. The first two categories of estimators can't handle unknown features at forecasting time. Modern neural networks like PyTorch forecast can handle them, but the training cost is higher for them as well. Time series forecasting requires special data splitting methods for holdout and cross-validation because the data are ordered by time. The task is to forecast the future for a certain horizon based on the past data, and not vice versa. So we need to make sure the data used for training are strictly before the data used for validation, no matter whether we use holdout or cross-validation as a resampling strategy. Let's look at some examples. Assume the forecasting horizon is 3 months. The training data have 24 months. For holdout, we use the last 3 months for validation, and the previous 21 months for training. For cross-validation, the first fold uses last 3 months for validation as well. The second fold uses months 19 to 21 for validation, and the previous 18 months for training. This cross-validation method is named forward training. There are alternative methods like sliding window. FLAML allows a custom data splitter to be used. No matter which method you choose, keep in mind the two principles. A, the data order needs to be preserved. And B, the validation data needs to be right after the training data, and the length needs to be equal to the forecast horizon. Now let's look at some example. Let's consider a simple case. The dataset has only two columns, the time index and the forecast label. Here we use a standard dataset for predicting the atmospheric CO2 concentrations. This dataset contains weekly averages of CO2 concentration ppmv in 44 years. We convert it into monthly data with this slide. So this their sample, yeah. So this line makes sure there are no missing values. Then we set the forecast horizon as 12 months. The training data frame has two columns. X-test is a data frame with days for prediction. Y-test is the true labels corresponding to the days for prediction. To use FLAML for forecasting, the code is very similar to other tasks. For example, we set the time budget as 240 seconds, that is 4 minutes. The optimization matrix, mean absolute percentage error. The validation method can be chosen from auto, holdout, or CB. In AutoML.fit, we pass the training data frame and the label column. This period argument is needed to specify the forecasting horizon. We plan to forecast for 12 months, so we set period equal to 12. When we run AutoML.fit for this training dataset, both regressors and statistical forecasting models are included in the AutoML run. In the end, a tuned Cerimax model is chosen as the best model and retrained on the full training dataset. We can find out more information about the best configuration by checking the best config, best loss, best config train time, etc. We can also visualize the learning curve for the AutoML process, as we demonstrated before. Then we can apply the trained model forecast by calling the AutoML.predict function. We can also visualize the predictions and compare it with the ground truth. You can find more examples in our documentation website. Okay, with that, I will conclude the section for time series forecasting. So, Jing, how good are we on time? Shall we move on and leave the question to the end? So you're on mute. You're on mute. So, yeah. So you're still on mute. Are you still muted? Can you find the mute button in the bottom? You're still on mute. So Louis, are you able to mute yourself?
Yeah, I was able to unmute. I'm
Okay.
not sure. Maybe she can't hear us. I just okay.
Yeah,
She's
yeah.
rejoined.
So both Louis and I can mute. So Jing, do you see the button on the bottom of your screen? The unmute button. It's not working. Okay, then maybe I can use this time to answer some questions. So there's a question from Jerry. Can you please repeat why we have repetitive timestamps in the date column? Okay, let's take a look. I assume you are referring to this slide, right? Yeah. Yeah, that's a very good question. So why do we have multiple identical days like these two? So if you look at the first column, the skill column, so that's a ID column for time series, right? So different values like skill number 1, skill number 2 correspond to different product skills in this case. So each product skill has its own time series, right? So for example, for this date, January 1st, we have the sales number for skill 1, skill 2 respectively, right? The same for the second date. So that means this single date frame can contain multiple time series, and the multiple time series are separated by the ID column, right? And this ID column is categorical. So I'm showing this data set as a generic case. Of course, you may have a single time series in your data sets as well, and you can just train time series models for each separate time series separately, right? That's also fine. It's just that in many cases, the original raw data set are probably not separated. So you might have the case where a single table contains multiple time series as a generic case. Yeah, that answers the question. Thanks. Are there any other question about the zero-shot part and the time series forecasting part, or even for the earlier AutoML or tuning API we introduced?
Hello, can you hear me now?
Yeah.
Okay, good.
Great.
Sorry about
Okay,
it.
no problem. Okay, so I will hand over to Qingyun for the next section.
So next, I will briefly talk about some ongoing and future work in FLAML. Some of these work are not mature enough, but that's why we want to hear from you to know how we should improve. And at the end, I will lead like around 15 to 10 minutes for discussion. The first work I'm going to talk about is about online AutoML. The objective of online AutoML is to automate the tuning process of online machine learning. I guess many of you may not be very familiar with online learning. So let me first briefly introduce online learning. Online learning is a type of machine learning paradigm targeting at scenarios with the following properties. In a typical online learning setting, data is only available in a sequential order as opposed to the case in the offline learning or batch learning setting where people usually assume there are data sets collected upfront. With its access to a data stream, the training and learning is also performed online as we have more and more data. And finally, the prediction or decision-making result of the learning algorithm also need to be evaluated online. This online learning paradigm is commonly used in interactive learning and reinforcement learning. For example, Rabbit is an influential online machine learning library which contains a large collection of state-of-the-art online learning methods. And one notable online learning product is Azure Personalizer service at Microsoft. It is a cloud-based service that helps customers application choose the best content to show their users. Online learning is a desirable learning paradigm to make predictions or decision makings in real time. But similar as the case in offline machine learning, effective online learning also involves the tuning of hyperparameters. For example, featureization choices, learning rate, regularization, and etc. This tuning process is now mostly done by data scientists, and the online learning services have a natural need for AutoML-style learning that automate this tuning process. But due to the unique properties of online learning, it is difficult, if not impossible, to directly apply those conventional AutoML methods to do the online tuning. The difficulty mainly caused by these three unique challenges because of the online learning paradigm. First, in a practical online learning setting, there is usually a sharp computation constraint that at any time point that, for example, in terms of the number of models you can train. This sharp computation constraint is usually ignored in conventional AutoML methods. Second, any functioning online learning system needs to be able to handle vastly different scales of data volume, which makes it non-trivial to decide how many data samples we want to spend on training a model with a particular hyperparameter configuration. And finally, the learning algorithms are being evaluated constantly, which is obviously not the case in a typical offline learning setting, where people are just using the final performance on a test dataset to access the quality of the hyperparameter. This online performance evaluation actually brings critical new challenges to online AutoML because it means in addition to the computation price of tuning, we also need to pay for the learning price for trying different hyperparameter configurations. With these unique challenges, the main research question is how can we best design an efficient online AutoML solution, which can find a balance between searching over a large number of possible choices such that we are able to cover a good one, and concentrating the limited computation budget on a few promising choices such that we do not pay a very high learning price. To this end, we proposed a champion challenger online AutoML framework, and I will briefly talk about our method in this with this flowchart. In our framework, at any time point, we maintain a pool of live models, which include one champion model and a list of challengers. Here, a champion corresponds to the configuration that is proven the best at any concerned time point, and the rest of the candidate configurations and consideration are all called challengers. The overall goal of this framework is to properly allocate the limited computation resource to try new challenges, and at the same time, we need to try to promote the most promising ones to be a new champion, such that we keep track of a good one to use. And this champion model will also be used to generate more challenges, such that we know which are the candidate ones to try. The final prediction is made with one of the models in this live model pool shown in this orange box. And we will make this selection with a model selection strategy. Because this champion is always in this live model pool, we have a theoretical guarantee on the quality of the prediction at any time point. For more details about this method, you can check our paper. Here I will show you an example of how to use this method in FLAML. In FLAML, we are implementing this method together with Bubble Rabbit, as I introduced before. It is a library for online learning. So I will just go through this notebook. So basically, in order to use this method in FLAML, it's called AutoVW because we are doing the automation for Bubble Rabbit. This is an online learning library. And to use it, you need to install FLAML and Bubble Rabbit related dependencies. And now I'm getting a dataset from OpenML. It is a regression dataset, and then I did some pre-processing to convert it into Bubble Rabbit's required format. And then I set this online learning loop. So basically, this online learning loop is to simulate this online learning environment. In this online learning loop, you can see that every time we get a new data sample, and then this online learning method needs to make a prediction. And then the loss will be calculated based on every single prediction and the ground truth in real time. And then at the end, we will calculate all the loss using a metric called progressive validation loss. And this block of code shows how to run a Bubble Rabbit. So basically, you just create a Bubble Rabbit instance, and then you do this online learning in this online learning loop. And with FLAML, you can directly import AutoVW from FLAML. And in AutoVW, you can first specify a search space and then specify the number of live models allowed. So in this example, I'm using AutoVW to tune the namespace interaction for Rabbit. So here in a namespace is basically a group of features in Bubble Rabbit. And tuning namespace interaction means that we want to tune the feature group interactions. Specifically, we are trying to add more interactions on existing singleton features. So this is how we do the online learning. So basically, you can use AutoVW the same way as VW when doing this online learning. And this blog shows the result of AutoVW. You can, from this printed message, you can see what are the interactions we generated. So basically, this A, B, C, D, those are the original namespace the name of the namespace, and those, for example, AH means that we are generating interactions based on these two namespace, which represent two groups of features. And then we calculated the final progressive validation loss. And this block of code compares the vanilla VW and AutoVW. Here, AutoVW NI means we are tuning the namespace interaction. And this result shows that we can indeed have better progressive validation loss, mainly because we can quickly identify the configuration with a higher order of interaction, which can do the online learning more effectively. And in addition to the namespace interaction tuning, we can also tune other type of hyperparameters. For example, in this example, I'm tuning both the namespace interaction and the learning rate. So then I just set the search space for learning rate to be a domain. So this is, if you still remember, we introduced the domain for FLAML. So here is the same. You can just use a log uniform or uniform domain to tune a particular numerical hyperparameter. And then the result, this is a progressive validation result by tuning both the namespace interaction and the learning rate. And this is a result configuration of all these three methods. So vanilla VW is the one without tuning, and auto VW NI is the one that in which we tune namespace interaction, and NI plus LR means we are tuning both in namespace interaction and the learning rate. And this result shows our advantage. If you have if you have more questions about this this example, we can discuss at the end. So then I will move on to the next ongoing work. The next ongoing work is about machine learning fairness in AutoML. So in recent years, with the adoption of machine learning in wide range of application domains, there have been increasing concerns about the fairness issue of machine learning, especially for application domains where the decisions have a direct impact on human. In fact, there are many domains where explicit regulation about fairness exists in the US. And in recent years, efforts have been made about machine learning fairness, especially since 2016. The research effort on machine learning fairness mainly focus on these two directions. The first type of effort is to try to come up with a better fairness definition in the context of machine learning, and another type of effort is to propose techniques to mitigate unfairness issue in machine learning. And with the adoption of AutoML in more and more domains, for example, the financial domain, it is very important to also take fairness concerns into consideration of AutoML pipeline. So we proposed to consider the problem fair AutoML. And the goal in fair AutoML is to find models not only with good accuracy but also fair. So, but this question is, although it is very important, it is still underexplored. A lot of questions need to be answered. For example, is it possible to find a model that is fair without applying any unfairness mitigation? And is unfairness mitigation necessary? And how to incorporate it into an AutoML pipeline? And if you can find fair models with or without unfairness mitigation, how the utility, for example, the accuracy and the computation cost will be affected. So all those questions are unexplored. And in this work of us, we take the initial attempts to answer some of those questions. So we first developed abstractions for fairness assessment and unfairness mitigation, such that we can easily incorporate existing effort on fairness definition and unfairness mitigation into an AutoML pipeline easily. And we also investigated the need and the impact of unfairness mitigation on AutoML. More specifically, our case study shows that AutoML itself can already find models with various degrees of fairness, but they are still not good enough in general. So the results shown in the first figure, the black dots shows the unfairness score and the loss for the points found in an AutoML process. So we can see that we have a large range of unfairness score. So if you do have a fairness requirement, you can actually find a relatively fair model. But if your requirement is very strict, then the number of fair models is very few, and also the loss is very bad. And we also looked at the impact of unfairness mitigation in terms of the fairness and the loss. So, but after applying the unfairness mitigation, we find that the models produced becomes fair, relatively fair, as shown in the second sub-figure of this figure. And this is the impact in terms of the loss. And we find that unfairness mitigation can indeed brings performance degradation in terms of the original loss. And the fourth figure shows the impact on the computation cost. And we found that certain unfairness mitigation techniques can indeed make the training much more slower. So considering this complex impact of unfairness mitigation into model training, the fair AutoML problem becomes non-trivial. In our work, we propose this fair AutoML formulation in which we explicitly take the fairness assessment and whether to perform unfairness mitigation into consideration. Based on this, based on our case study and our problem formulation, we proposed a general fair AutoML framework. In this flowchart of this framework, the components shown in black are the components from a regular AutoML pipeline. And on top of it, we enable the input of fairness assessment and unfairness mitigation. Note that you can leverage existing effort on fairness definition and mitigation. For example, FairLearn provides a very comprehensive set of existing definitions and existing mitigation techniques. And then these two procedures can be incorporated into this model evaluation and the model building process. In addition, since it is not necessarily good to always perform unfairness mitigation, we introduce this fairness manager into this pipeline. The responsibility of a fairness manager is to decide whether and when to perform unfairness mitigation. This framework is quite general and is compatible with most existing fairness definition and unfairness mitigation techniques, and also most of the existing hyperparameter searcher. This is a very desirable feature because fairness definition is usually very context and application dependent. So different people and different use cases may want to use different definitions and different unfairness mitigation techniques. This framework allows you to do it very conveniently. And based on our proposed fair AutoML framework, we realized a fair AutoML system called fair FLAML. In fair FLAML, we proposed this self-adaptive strategy to make a decision about when about whether and when to perform unfairness mitigation. Basically, we have a strategy for fairness manager. And this figure shows a preliminary result we get in terms of fair loss on the adult dataset. In this dataset, the sensitive attribute is sex, and we use a group fairness definition called demographic parity as the fairness metric. And our preliminary result shows that we can indeed achieve a much better fair loss than AutoML systems that is not considering fairness, for example, FLAML, and the fair BO, which is a method which takes the fairness constraint as a constraint when doing hyperparameter optimization, but it does not leverage unfairness and mitigation techniques. Here, the fair loss is the loss of the models that satisfy the fairness constraint. So for more future work, I would like to highlight some open problems motivated by the current deficiencies of AutoML. First, regarding the performance and the customization, customizability, some open problems include, for example, what is the most efficient way to do multi-output AutoML? How shall AutoML find models that can generalize well over time? And how to perform AutoML with multiple optimization metrics? And regarding the comprehensive end-to-end support, transparency, and interpretability, the open problems include, for example, how to incorporate deployment constraints into the AutoML loop efficiently, how to automatically find not only a model but also a guardrail to a consumer, and can we estimate how long a given task takes AutoML to find the best model? And finally, I want to highlight that this project welcomes and encourages all forms of contribution, including but not limited to pushing patches, code review, documentation, community participation, tutorial and talks, and sharing your application scenarios and feedback. And there are multiple types of contribution opportunities you might be interested in. First, you can share your use case and needs, especially the needs that are not well satisfied by our current feature. In this case, you are encouraged to connect with us on Gitter to discuss what improvements you want to see. And if you are already familiar with our library and clear about what improvements should be made, you can also directly create issues. And second, you can also make a development contribution to help improve existing immature features, or help add new features, especially the ones you need. For example, the zero-shot AutoML, time series forecasting, online AutoML, and the new features include computer vision tasks, multimodal model, fair AutoML, and visualization and explanation. Finally, integration with other open source libraries is another way to contribute that may be interesting to you. We have successfully integrated Ray and ML flow to FLAML to help with parallelization and logging. If you find some library especially helpful in your workflow, you can consider integrating them into FLAML. Of course, if you can also integrate FLAML, AutoML, and Tune module to other libraries. For example, they are integrated into AutoCausality to help with AutoML and causal model tuning. And if you are interested in contributing, please connect with us on Gitter, and you can also find contributing guides and upcoming feature roadmap via these two links. And finally, I would like to have a discussion on some of the questions we mentioned earlier, and also answer questions.
Hey, Jane, have you gone over the questions?
Okay, yeah, maybe I can briefly go through the questions, and if you have something to say about any one of them, you can directly enter that in chat. So the first question we would like to discuss is, what challenges did you encounter or do you foresee when using AutoML or trying to use AutoML? For example, if you are not using AutoML or auto-tuning, what are the barriers that hinders you from using it? And the second question is, what additional features do you hope to see in AutoML? We have identified some of them when I talk about the opportunities for contribution. For example, the new features include computer vision tasks, multimodal model, fair AutoML, visualization, and explanation. Is there any particular one that you hope to see or you find might be very useful? And you are also welcome to propose new ones beyond what I just mentioned. And the third question is, what kind of human-computer interaction is desirable in the AutoML process? So this question is motivated by the survey, some content in the survey. The survey paper mentioned that that human in the loop AutoML should be encouraged, but there is a subtle dilemma between the need of automation to save human effort and the need of involving human input and human expertise. In your scenario, which part of the machine learning workflow do you think human inputs are especially useful or necessary? For example, currently the problem formulation or framing part is almost always need human input. Are there any other components like this? And the fourth question is about online AutoML. We have done some preliminary work on online AutoML, but we want to know, do you use online learning in your scenario? Do you find online learning potentially helpful? And if you are using online learning, what kind of libraries or tools or tuning tools are you using? And about fair AutoML, is we want to know, is fairness a valid concern in your scenario? If so, what is the current practice for dealing with it, especially in the context of machine learning? And finally, we want to know, we would like to ask, what are the takeaways you get from this tutorial? And we hope to learn from your feedback. Chi, you are muted. Are you talking?
Oh, sorry about that. Yeah, I was saying that I can answer some questions earlier in the chat. So like Ethan asked for the natural language models, like bird-based models, does FLAML fine-tune the embedding layers of bird and not just the classification layer? Feed forward the hyperparameters. Yes, the answer is when we do the fine-tuning, we will retrain the model using the new label data set for your specific task. So all the layers in the network will be updated. The hyperparameters, though, are not separated for the classification layer and the embedding layers. The hyperparameters are used for training the entire network jointly. So if so that's my understanding of your question. My understanding of your question is about the parameters updated in the network and not about hyperparameters. But you have but if that interpreter is not correct, please ask the question again and let me know. Yeah, thanks. So
it seems I can now see the chat. So if there are any discussion or question there, can you raise them?
Oh, okay. So Jerry asked, can you please define fairness of machine learning in general, or what kind of fairness are you dealing with?
Yeah, so that's a good question. So as I mentioned, the current research on fairness of machine learning is actually one of them is basically discussing what is a good fairness definition. So there is no like converged answer on this question yet. But the typically used fairness definition is a type of definition called group fairness. So basically, the group fairness is trying to make the, for example, the errors you made on different groups of people to be equalized, such that you are treating like the different group of people the same way. And another type of definition is called individual fairness. Basically, it's trying to it does not depend on a group attribute. Basically, it's trying to treat every similar individual the similar way. So in our work, we are for example, in our this evaluation, we are using a typically used fairness definition called demographic parity. So it is a typical fairness group fairness metric based on a sensitive group attribute. Yeah, hope this answered the question. And I want to mention that this this fair automa framework is not coupled with a particular fairness definition. You can whatever definition you use, you can easily include that as an input, and then in the fairness assessment part, we'll just use that definition to access fairness using your preferred definition.
Thanks. Next question from Yunfan. Is it possible to apply AutoML in generative model building in the synthetic data generation area in the future?
Synthetic data generation. I guess I think it's possible, but it depends on how you formulate the problem. For example, you need to have a very explicit goal of what is the synthetic, what you are looking for. For example, are you looking for a synthetic data which shares the same distribution with a particular real data. Then you can, once you have a clear definition of your goal, you can always use AutoML to tune your hyperparameters or tune some choices to try to generate a good synthetic data.
Yeah, I would think the Tune API introduced earlier by Qingyun would be the right feature to use.
Yes.
In this case, for example, if you think about GAN kind of techniques, right, to generate synthetic data, you can define your GAN process in a user-defined function and return some metric about the quality of the generated data. So you need to have a metric to measure that, and you also need to specify hyperparameter on the search. So once you have all these, it should be easy to just apply the Tune API and tell what metric you want to maximize or minimize, what search space you have for scan models, for example, right? And do the tuning. So Jimmy, maybe you could paste the link for the tuning API in the chat.
Okay.
Yeah.
The link for the tuning API.
Mm-hmm. The tune use case in our documentation website. And in the same time, Jerry has a question. In my current research, we are investigating the fairness of ML-related digital objects. It is about digital objects.
Digital objects.
Yeah. It's about data readiness. It seems like a different aspect of fairness. Thanks for your explanation.
Okay. Data. Yes. Data. Okay. Yes, it's possible. So basically, in that case, the data is, for example, the fairness definition or similar concept is defined based on purely the data set, right? So basically, it's a measurement of the data set. For example, how unbalanced is this data set can be an indicator of something related to fairness. So they, in that case, it can be readily considered as a fairness metric in our framework. Any other questions? Chi, you are muted. There is no other questions, right?
Yeah, I don't see new questions in the chat.
Sure. Then maybe we can end here because we have used up the time.
Yeah, hope everyone enjoyed the 3-hour workshop. A lot of content, and you can reach out to us at Gitter or send us emails. So shall we? Yeah, I already shared the Gitter link in the chat. I can also share my email address.
Yeah, can you also type my email address?
Sure. Could you say
qingyun.wu@psu.com.
Okay. Yeah, or like message us directly on this website. Yeah. Okay. Thank you, everyone. Appreciate for your attention. Thanks for staying until now.
Okay. Thank you. Thank you. Bye.
Appreciate it. Have a good day.